Welcome back. This is the last class of this course, and we will discuss this downlink synchronization. Okay, and we'll see how it goes. So, and what we are going to discuss is downlink synchronization for FR2. Okay, and whatever else, I told you also what is common for FR1 and FR2, but as a part of this, it will become more clear. Okay, and we'll see how this beam selection, what is this beam selection, and then how is this subframe boundary detection done. Okay, so now what we discussed in the last class was that for FR1 systems, base station basically needs to broadcast the SS block. Okay, and how it does is basically it with multiple antennas, let's say 64. It uses special precoders to broadcast this SS block in all the directions. Correct? Okay. Now that is done at the transmitter. After that, I have not told you how does the user uses this information to do the frame boundary, okay, or the slot boundary acquisition. I have not told that. I'll do that. Okay. But before that, this broadcasting, okay, is done for this broadcast signal is done for FR1. If you do this broadcasting for FR2, you know that it will never reach the user because the channel is hostile. You essentially need to form these pencil beams or the sharp beams towards the user. Correct? Okay. Now you will form that, okay, but the base station doesn't know where are the users, right, in the cell. Okay. Right, so it does something called beam sweeping. Okay, that's what I'm going to show you. Okay, how does that happen? Okay, so what happens here is that I showed you this diagram. Okay, we assume that when I showed you last time that base station knows that user is located in this direction. Okay, but what are we talking now? We're talking now about the initial access where base station doesn't even know user is located in this direction. Okay, right? Okay. So as a part of this initial access process, wherein even before a user can do slot boundary acquisition, right? Okay, it has to basically should have that enough signal strength in FR2 to do that, right? Okay, correct. And that's what this makes it initial access different for FR1 and FR2. Whatever I'm going to show you now doesn't happen in FR1 because the signals are getting broadcasted. Okay, so user located anywhere in this cell will be able to receive that signal with sufficient strength. Okay, in FR1 system. But for FR2, if base station, let's say, transmits in this direction, but the user is in this direction, it will never be able to receive the synchronization signal. Correct? Similarly, if it does in this direction, transmit the signal in this direction, user will again not be able to receive the signal. Okay, right? So this part, what I'm going to discuss, will help the user in basically doing this kind of beam attachment. Okay, so I'll show you that. So you see this. Okay, what is happening here is that this synchronization blocks, okay, right, are being basically transmitted. This is synchronization block 1. It's transmitted in this direction with using one sharp beam. Okay, if the user is located here, okay, then user will be able to receive the signal from this direction. The user is not located here, that can happen. Okay, so what it does is, keeping this in mind, user retransmits this synchronization block, okay, with certain changes which are specific to this beam, okay, in this direction, and it does in this direction, does in this direction. Keeps doing that. Okay, right? So a user located here, as I showed you in the last slide, will be able to basically synchronize to this beam. Okay, so and this is a base station has to continuously keep doing that. Okay, right? So this problem doesn't happen in FR1. Please understand that, because in FR1, even if you broadcast, okay, that users will be able to receive the sufficient signal strength because the channel is not that bad. Correct? Okay, but this is mandatory in FR2, wherein the signal strength becomes very bad because of the hostile channel. Right? Okay, so this is a key difference between FR1 and FR2 synchronization. Once user sees that it has to get connected to this beam, Then after that, the process is same between FR1 and FR2. I'm talking about the synchronization process, which will be same between FR1 and FR2. At this stage, they are different. Okay, and the difference is because the FR2 has a hostile channel, and that we need to form these sharp beams. Is this idea clear? That how initial axis is different between FR2 and FR1. Okay. Underneath this, once this beam selection has happened, everything is same. Okay, right? And the reasons are obvious. Okay, that because of the hostile channel. Okay, so now before I tell you that how this user creates this beam in different direction, and the base station creates this beam in different direction. Okay, we are looking at this line of sight channel. Okay, I'll just tell you how this beams are created in this different direction. Okay, right? Because how will this beam be created? Base station is using some precoder to create a beam in this direction. This will be precoder W1. This will be some other precoder. This will be some other precoder. But this precoder, I'll show you, is very different. It's very easy to understand how these precoders are created. Okay, so I'll take you to this particular figure. Okay, what are we saying here? There is this user located in this particular direction. Okay, we are looking at the line of sight channel, right? Okay, what are we saying here? This is the base station receive antenna. Okay, I'm just looking at the uplink. Same thing is applicable for the downlink also. Okay, so what is this? Is antenna 0, antenna 1, antenna. There are M antennas. Okay, in the base station. So what are we saying here? Now this is a line of sight channel. You see there are no scatterers. Okay, so base station, the user radiates some signal in the uplink. Okay, what I'm looking at in the uplink, but same thing I said is applicable in the downlink also. Okay, so user is in this direction, sends a signal. This signal is received by different antennas. Okay, right? Now you see this, between this and this signal, there is a certain path difference. This signal has to travel a longer path than this. Look at this, and what is this difference between, if you drop this perpendicular, okay, this, between this and this path, okay, this is the difference. I'll show it to you. Okay, this is the difference. Where did it go? Yeah, this is the difference. Okay, right? And what is this difference? Where is this difference? This, essentially this. Okay, right? Now this is the distance between two antennas, DH. Okay, correct? Now if this is DH and this is the angle being made by the user phi, this is the user and this user is making the angle phi. Use simple trigonometry, you can find out that this is basically DH sin phi. If this is DH, okay, right? So what is this? What am I saying? This is the path difference between this and this. Similarly, there will be this path, same path difference between this and this, same path difference between this and this. Okay, right? So what does the path difference lead to? It leads to, between two rays, electromagnetic rays, it leads to phase difference, right? Okay, what is the phase difference between when there is a given path difference? Phase difference will be 2 pi by lambda into the path difference. I am saying phase difference will be equal to 2 pi by lambda into path difference. Okay, so if you look at the channel between this antenna and this antenna, the line of sight channel I am talking about, okay, what will be the difference between these two antennas? Only the phase. And how much will be the phase difference? 2 pi by lambda into path difference. Correct? Okay, and this phase difference, this path difference will progressively increase between this and this, between this and this. Right? So if we consider that this has 0 phase, okay, this will have how much phase? 2 pi by lambda into d sin phi. Correct? So that's what I have written over here. Okay, so what have we done here? We are basically, so you look at this, what is coming over here? This is the channel of the first antenna. I am written as 1 because that has 0 phase, e raised to power j 0. That's what I am looking at. Okay, what will be the angle of this? What will be the channel of this? 1 into e raised to power phase difference, right? J phase difference. And what is the phase difference? 2 pi by lambda into dh sin phi. I have set lambda to 1, okay, right, just for the convenience. Okay, what will happen? So what will be the phase difference between first antenna and second antenna? 2 pi dh sin phi. What will be the difference between m minus 1th antenna? 2 pi m minus 1 dh sin phi. So this is your line of sight channel. Okay, in which direction? In direction phi, correct? Okay, and this is very easy to find out. Okay, right? Why? Because if you have to create a beam in particular direction, and what is the direction? Phi. You know the channel already, line of sight channel. Correct? This has nothing to do with the user location or anything. This is simple line of sight channel. Okay, what am I saying here? Let's go back. If you have to create a beam in this direction, correct? How will you beamform? You will take Hermitian of this channel, right? That's the precoder you will use, correct? If you have to beamform in other phi 2 direction, you will take this channel with phi 2. You will have to create, then if you have to create beam in other direction, right? Okay, you will use that angles, right? Phi 3, okay? So what are we saying here? To form a beam in particular direction, base station uses this channel. It doesn't have to estimate this channel. This is simple line of sight channel, okay, which I have given it to you, correct? Okay, and this is a channel in a particular direction, right? So if the base station forms a beam and wants to form a beam in direction phi 1, it will multiply its, what will be its precoder? Its precoder will be Hermitian of this, right? It will form a sharp beam in phi 1 direction. If it wants to form a sharp beam in phi 2 direction, you change the angle to phi 2. That's what I am saying, okay? To form a beam in a particular direction phi, base station uses this channel using maximal ratio phase only uplink or downlink beamformer or combiner or the precoder, okay? So that's what I showed in the last slide. What will base station do? Hermitian of this in particular direction. That's the precoder it has to use. And if it has 64 antennas, beam will be pencil beam. If it has 32 antennas, it will be slightly broader than that. But it's very easy for the base station to create these beams for line of sight channels, and that's what it can do because it does not have any other information about the user. It is blindly sweeping these beams in particular direction, right? Okay, so this is, as I said, 1, this is phi 2, phi 3. It knows the precoder for all of them. In one slot, it will sweep in this direction, in another slot, it will sweep in this direction. Okay, right? So this is primarily the idea. Okay, now using this, I will show you. This is a work which I did with my dual degree student long time ago. Okay, that how this initial downlink synchronization is done. Okay, using an example system. So this is an example 5G system where both base station and UE have n antennas and one RF chain. Simple. Okay, it forms four beams. User also forms 4 beams. Okay, right? Because user also needs to like form this beam, right? Okay, so then how many? What are we saying here? Both of them employ 4 beams. Okay, base station forms 4 beams. User also forms 4 beams to collect those signals. Okay, and we use 512 FFT. So it's just an example, okay, system example, a simple system example. Okay, so if you can do that, like in this 0.5 millisecond, if you take 512 FFT, a slot has 7680 samples. Okay, if you consider 64 point a certain CP of 32 or 64 point. Okay, so a slot will have 7680 samples. Okay. One SS block will have how many samples? Because one SS block is only for half of this slot, right? It will have half of this sample, 3860. Okay, right? So now this is simple, 512 7680. How does it come? We'll do this. Let me do this. So what are we saying here? That this is 512 FFT plus 36 CP length. Okay, 548 samples it will have. Okay, and each CP plus the FFT length. Okay, then the first symbol will have some additional 6 samples to make it this 7680. That's all. Okay. So if you, so 548 into 14 plus, well, the first symbol will have additional 8 samples. Okay, that's what makes it 7680. Okay, 32 length CP for each symbol, 8 additional samples, right? Okay, for sorry, it was 36 samples, CP samples for each symbol. That makes it 548 plus 8 additional samples for the first symbol. That's what will make it 7680 samples. Okay, right? Because we know that first symbol will have some additional samples. So one SS block will contain 7840 samples. Okay. So what is the problem we have? There are like total of 16 beam pairs, and UE needs to identify the best beam, best transmit beam and best receive beam. Okay, right? And time domain transmit signal for one SS block consists of how many 7 OFDM symbols? Right? That's what I showed you. Okay. So what is this? This is X of M. This is the, you remember, yeah, the transmit domain, transmit symbol. Okay, and then it is precoded using a precoder in particular direction. Okay, correct. And this is the precoded signal. That's what is being transmitted. Okay. So XM are the samples of time domain signal for one SS block. Time domain, precoding in time domain, precoded signal. That's being transmitted in a particular direction. SS block, precoder in a particular direction, which I just taught you how to transmit in a particular direction. Right? This is the signal being transmitted in one here. Okay. Base station will also generate this because it also has same number of antennas, n antennas. User will also generate this precoder in a particular direction. Right? That's why I said how many such total beam pairs are there? 16. 4 base station will generate and 4 user will generate. Okay, it has to figure out whether this beam pair is best, or 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 this. It goes on like this. Right? 16 such combinations are there. Okay, right? What do these 16 combinations tell us? Which is the best transmit direction and which is the best receive direction? Because at the beginning, none of them is aware of that. Neither base station nor user. Okay, right? So this is the transmit precoder. Right? So this is hiding. This W is the transmit precoder. Okay. So what is the time domain signal received by the user? Precoded signal plus noise. What will user do? It has received some signal, correct? It will multiply with the receive combiner in a particular direction. It doesn't know, but what it knows is only it can generate only 4 beams, right? Okay, it can combine only in 4 receive direction. Base station is transmitted in a particular direction. User is combining in from a particular direction. Okay, receive beam forming vector theta r, receive beam steering angle. How will it generate? I gave you a formula. A line of sight system, right? What was that? 1 then e raised to power j2 pi, that vector. Okay, Hermitian of that, you put it over here in a particular direction. So what are those different angles in which user and base station will generate? Minus pi by 4, minus pi by 8, pi by 8 and pi by 4. These 4 directions, they are generating the transmit and receive beam. You can generate in more directions also. I am taking a simple example. Okay, this is AWJ noise. Now what happens? Okay, in this y of m, what is contained? X tilde of m, and X tilde of m contains what? Precoded PSS sequence, correct? Okay. Now user knows that there are only one of these sequences, okay, correct? And I am assuming that base station user knows that a particular PSS sequence is being transmitted. Okay, we are not considering all the sequences just for simplicity. Okay, otherwise this complexity will increase. So let's say PSS 0 is being transmitted, base station knows that and the user knows that. Okay. So now what it does is it pre-generates this PSS sequence 0 S of k of length 548, because what is it? It has to do this operation in time domain. How much is the length of the symbol? 512 plus 36 CP, 548, right? So it stores that. It uses these samples to correlate with the received sample to detect the PSS, okay, right? And how many times it will do this operation, that's what you have to see. Okay, so what is this correlation? This is the sequence, 548 length sequence generated at the receiver. This is the signal being received by it. Okay, R is what? Received signal after combining. What is Y of M? Signal, precoded signal transmitted by the base station plus noise. Okay. So what is it doing? It is correlating PSS 0, local copy of PSS 0 with the received signal. Okay, and I'll show you what. Look at this. This is what. And how many times it will have to do this operation? It will have to do this operation 16 times, because how will it be done? Base station will basically transmit in particular direction. What will user do? User will use 4 different receive combining vectors in 4 different directions. 4, base station changes it, user again does it 4 times, third time and 4th time. So how many such different times base station user has to do? 16 times, right? Okay, fine. So if it does this and saves this operation, these correlations somewhere, right? So what is this? You see this. This is first, second, third, fourth. Those 500. What is the correlation? 548. 548. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, right? So what is it telling? Peak denotes the presence of PSS sequence in the received signal R of M. What is it telling? That this particular direction is basically the strongest. Right? Look at this, because base station is not located in this direction. It is located in the last 4th transmit beam and 4th receive beam. That's where it is located. And you see that you find out the maximum. It will tell you that this is the best beam pair, looking at the correlation. Right? Okay? So time sample of the peak denotes the start, and where will this happen? Okay, because you do this operation wherever these PSS exactly align, and where will they align? They'll align at the start of the OFDM symbol, right? So the start of the peak gives you the start of the OFDM symbol where the PSS is located. And the maximum peaks tell you which is the best received pair, right? Okay, so what have we achieved with this? 2 objectives. That for FR2 system, we need to have this best receive beam pair, transmit and receive beam pair. That is being done by doing this operation 16 times, right? Okay. Now if it is FR2 system, it is broadcasted, right? Okay. User doesn't have to do all this. User will do it only once, and the start of the boundary will tell you what is the OFDM symbol. That's all. Okay, right? And what have I done? 3840 into 16, right? How many samples? This is, you are storing 3840, half of this slot, right? And how many such slots? 16. 61440 samples corresponding to 16 synchronization block. Gotten it. I've given you one part of it. I have not told you how frequency offset estimation is done. I've still not told you. I will not be able to tell you also. Okay? But this should be clear that this operation is particular to FR2 operation, wherein what is this operation? Finding the best beam pair. In FR1, most of the time you don't do it. Okay, because channel is much better than FR2. Okay, so before I go here, okay, this is the end of the synchronization operation, which we can cover in the class. But there is, as I said, there is downlink frequency offset estimation, there is uplink synchronization. After you see this, you can learn about it by reading papers, by reading books. Okay, that I will not be able to cover in the class. So I will quickly summarize whatever we have learned in this class. Okay, so what is this? What was our focus on in this class? MAC layer, okay, we looked at one entity in the MAC layer. What was that? Which is very important for a scheduler, right? Okay, we learned about different kind of schedulers, but beyond that, we did not get into the details of MAC layer signaling, how MAC processes its data, right? What we know here is this is what comes to the physical layer: transfer block and control information. We learned most of it of how this processing is done, okay, about PDSCH and PUSCH chains, okay, then PDCCH and PUCCH, right? Okay, we covered to a good extent, okay, right? We saw all this can be done in this course. Then we learned about MIMO transmission, how 5G enables MIMO. And then we learned about the fundamentals of MIMO transmission also in context of this, right? Because to understand how MIMO is implemented, for the students who have not done this MIMO transmission, we briefly touched upon it to figure out what aspects of MIMO are relevant for 5G, okay? So we looked at the end of this, this course teaches you that how this physical layer processing is done for these three aspects, okay? Right? And beyond that, if you want to learn, this course has enabled you to figure out things on your own by reading different papers, by reading different books, okay? We'll stop here. This is the end of this course, and thank you for attending.